All right, good morning. We're getting fewer and fewer students. Maybe it's related to this fact, I don't know. Yesterday, late, around 9 p.m., I've decided to check on the homework, and this is just homework one, part one. There's also part two, part three, part four. We can see some people finished it, but also we can see some people didn't even start it. And there is no law which directly relates the time when homework is started and the grade for the exam. But based on my experience, students who start late have a higher risk to get a lower grade. And that's why 7 lectures ago I made a suggestion and advice. Yeah. Don't wait until the last day. Start early, do homework every day, little by little, as much as you can. But that's just an advice. I cannot force anybody in doing that, right? It's like taking a cooking class. The instructor tells you, use those ingredients for your recipe. But you choose, do you want to use those ingredients or not? Just keep in mind, that's your choice. If you make a choice, you take responsibility for the results. That's a general rule. Also works for solving specific problems in physics, in life. And today and tomorrow, we're not going to learn anything new theory-wise. We're going to more practice. Practice makes things better. So tomorrow, I plan on having time for your questions. And probably tomorrow, I'm going to start a new topic, which is not related to this exam, but we have to start it anyway because we have to. So, question. A very typical situation, several resistors connected differently, and the whole circuit is completed. There's a battery, there's electric current. We need to calculate everything we can. But first, we need to make a statement about 2 resistors, number 1 and number 3. This is a review question. We had a very similar question about the capacitors. Yeah. So we remember that when we have 2 elements in a circuit, they may be connected in series, they may be connected in parallel, but they may be connected in neither way. So if we look at the resistors 2 and 3 and 4, they share the same electrodes. So these 3 definitely are connected in parallel. And that means a simple thing. Because they all are identical, we can replace all these 3 with 1 equivalent, which is equal to 1/3 of any of those. Of course, we can always calculate, like 1 over R equivalent should be equal to 1 over 15 plus 1 over 15 plus 1 over 15. But because they are identical, and we know the rule, it will be same result. And we can redraw the circuit. And these two elements clearly connected in series. But the resistor number 1 and the resistor number 3 are not. This is a junction point. When devices connected in series, there should be no junction point. Well, of course, now it's very easy to finish the calculation, right? So, for example, electric current will be equal to 24 divided by 3 plus 5, 8, 3 amps. And now, when we know electric current, that's an additional variable we just have found. Now we can just calculate anything. We just have to write an equation, plug the numbers, take a calculator, calculate. For example, power. Yeah? For the power, let's say, of the resistor number 2, what can we use? Well, nothing so far. We only know the resistance, 15. But for the power, we need to know two variables. So, for example, voltage or electric current. What's easier? Well, of course, we can calculate all of them, but what we know is this electric current, which in the circuit is counterclockwise, and this electric current splits at the junction I2, I3, I4. How does it split? Evenly. When we have all identical resistors, they should have the same electric current traveling. Can we prove it? Yes, we can. Because they connected in parallel, they also have the same voltage across. Same voltage, same resistance means same electric current. And if 3 amps splits in 3 equal parts, that means each electric current, I2 or I3 or I4, should be equal to 1/3 of 3, which is 1. So if I know electric current, now I can calculate power. I squared times R, 1 squared times 15 watts, etc., etc., etc. So nothing really special now. Search for the equation, write it down, plug the numbers, take a calculator, calculate. But I've used certain shortcuts. I didn't use actual algebra for calculating the equivalent resistance or the individual current, because I know what should happen. Yes? Yes, but there's an easier way. Yes, but there is an easier way. Which one? What do we know about the battery? Voltage. So to calculate the total power dissipated by the battery, you can just use the original 24 times 3. Which do you choose? Doesn't matter. You know, it's a matter of kind of practicing to see which equation works faster, but they all work equally correct. All right. What do you think about this situation? Again, we have a battery and 3 different resistors, one with an unknown resistance connected together. And we need to say something about electric current through the top resistor. We have 2 different approaches. Number 1, actually solving, doing algebra, writing equation and calculating that current, and then look at the number. And we will. But to answer this question, we can use a different approach. We can reason just what is happening with electric current when it goes through a junction point. So you have to choose your answer, because I want to switch and see what did you enter. And then I'm going to switch back. All right, so I just want to remind you, 2 days ago I sent an email with, I think, 1-800 phone number of the WebAssign. Those people promised me that if anybody has any issue with using WebAssign, just have to call and they will help you to fix it. That was the question number 3. Well, so first of all, we have to make a statement about the current approaching the junction point. So this electric current I is equal to what? Someone from the back. What is the number? What is the value of electric current approaching the junction point? Well, you're technically in the middle, but thank you. 5, how do you know? You have eyes, you know numbers, you can read, you see how many functions are involved. Yeah, but then it splits. So it means only a portion of it goes through each. Right? Right. Am I always right? No. But I'm pretty confident about this statement. So clearly, when you reason through, you see less charge traveling through the second resistor. So the right answer is 3. And if you choose 5 or greater, ask yourself, why? That's an important question. It's called the reflection in psychology. Well, now, of course, we can just solve this whole thing. Well, we know that according to the junction rule, if we add these 2 currents together, you should get 5. What else do we know? Well, we know that Anybody? Please tell me what a specific equation can I write down? I'm not looking. I'm listening. It's your time. Cannot hear you. That's not an equation. An equation has to have two parts. Something is equal to something. Equals I. Okay. That's not a specific equation. That's a general equation. When we need to write a specific equation, we have to write it specifically for a specific device, a part of a circuit. So, so far, that's not really helpful. You could write it specifically for a first resistor, for a second resistor, for a third resistor, or for the whole circuit. So you could write 4 specific equations. And if you're not sure what to do, that's what you have to do. You just have to write 4 specific equations, 1 for each specific element. So write it down. If you know what to do, you just do it. This is a difference between a problem and a task. Yeah. If you know what to do, you just do it. It's not a problem, it's a task. The problem is when you have to achieve a goal and you don't know what to do. That's a problem. In that case, you just have to start trying again and again. Because until you solve a problem, you don't know if your approach would be successful. So you have to try and then and again. So, and in this situation, trying means just using this law as many times as you can, hoping, or I say believing, it will work. If you truly believe, it will work. So, for example, how would we write a specific law for the resistor number 2? General. Specific. The specific law must have exactly the same structure, so it should have exactly the same variables with a little differences. Yeah? Structure. The fraction bar remains, equals, remains. What should I write for electric current? What should I write? Just I? I'm I'm writing for the second resistor. Let's call them again 1, 2, 3. But yeah, I thought it would have been clear. 2 ohms, second, 3 ohms, third. And also they go from left to right. For the second resistor, we don't know the electric current. We cannot write a number. But what do we write? Can we just leave an empty space? No, we can't. So we have to write something. But better if you write a symbol which represents. Can I just write an I? Gentleman in a hat. There's only one, no, 2. Oh no, that's not that lady. Okay. Gentleman in a hat, please tell me, can I just write a letter I? So you should have said no, because that would answer my question. And then you could say you should write A2 to represent a specific electric current, not just general. Here we should write R2 or the value. What should I write in a numerator? So far, nothing. I have no symbol for this voltage. So now I'm forced into introducing that symbol and then using that symbol. And, well, that's it. That's all we can do for now. Now we can write an equation for the third resistor. And this is what everybody should have written already. Yeah? You know the strategy. Now we can write well, let's be as accurate as possible. So delta V1 over, we have to introduce that symbol. R should be equal to 5 amps. Well, what else can we write? For the whole circuit, 16 over R equivalent should be equal to 5 amps. We could calculate the equivalent resistance, well, calculate in quotes, because we don't know R. Let's write it R1 actually. Let's be consistent, R1. And, well, we can write an equation. R equivalent should be equal to R1 plus, it should be equal to the equivalent resistance of two resistors connected in parallel. So, how do we calculate it? Well, it should be 1 over 2 plus 1 over 3. And in the end, we have to flip it. So, that's going to be the equivalent resistance. If we knew R1, of course, we could, yes? When you add the currents together, it will be. Hmm?
Just the equivalent resistance.
That's a good question. We could do 1 over R2, 3 as 1 over 2 plus 1 over 3, which is 5 over 6. And that would give us the equivalent resistance for only 2 resistors, 2, 3, 6 over 5. That's another possible relationship. There's one more relationship, which is very important and saves a lot of time, which is still not on the screen. And everything I've been doing here, I was just stalling to give you time. Because nothing from this is really important. Yes? You could do that. Perfect approach. There's also still one important statement, which, if I made it, would save a lot of time. And that is not mathematical statement, that's a physical statement about a specific type of a wiring, about a specific type of connection we have. Yes? Absolutely. When we have two elements or more connected in parallel, they have the same voltage across. So that's the same thing. So if we use this approach, we can calculate electric current faster, because on one hand, I2 plus I3 equals 5. On another hand, because of this relationship, the voltage is the same. Hence, 2 times I2 should be equal to 3 times I3. So the current splits, and naturally, the resistor with a lower resistance has higher current through it, because electrons are smart. Why would they go through the harder path if they can go through the easier path? So what two numbers can you suggest? On one hand, if you add them up, you get 5. On another hand, if you multiply that number on 2 and another number on 3, you get the same number, the same result. Anybody, please? Yes. 2 and 3, which is which? So this electric current, I2, should be equal to 3 amp, and this electric current, I3, should be equal to 2 amps. Technically, what we've done, we have solved a system, 2 equations, 2 unknowns, 2 equations. The equation number 1 and the equation number 2. We could have done it algebraically, of course. Solve one equation for one variable, plug it into first equation, solve it, etc., etc. But with these numbers, the answer is simple, 2 and 3. And, well, we also could do that. And now we can calculate anything else. Anything else. For example, voltage number 2, which is equal to the voltage number 3, should be equal to 6. 2 times 3, that's the voltage, 6 volts. Which means if we take the whole voltage, 16, and we subtract 6, it gives the voltage left across the first resistor, 10. And if we know voltage 10 and current 5, the resistance will be 2, right? So we always have more paths, more approaches to solve a problem like that than we need. And you should try all of them, just see which makes you feel more confident. All right, so a more complicated circuit, just to demonstrate a general approach. Now we have 5 elements, 1 active, 4 passive, and first we need a strategy, and the strategy is we have to make a step-by-step transition from the original complicated circuit to a circuit which has only 1 battery and 1 resistor. R total or R equivalent, same things. How do we make these transitions? Step by step. So we're looking at the circuit and we're searching for elements connected either in series or in parallel, for sure. And we can see these two connected in series. So we can replace. That's a step number 1. Every time we make a step, we change something. We have to redraw the circuit. We have to draw a new one. Now we only have 3 passive elements left. 110, 180. These elements haven't been even touched, so they remain the same. And this should be equal to 470. So we start searching again, and we're looking at the circuit, and we see another uh, elements which now connected in parallel, which means now we can replace these two with only one. The resistance of this resistor should be equal to 1 over 180 plus 1 over 470, and we have to also flip it. So this is the resistance. And now we can make the final transition. And the final transition tells us the equivalent resistance, total resistance of the whole circuit should be equal to 110 plus, well, whatever it is, 1 over 180 plus 1 over 470. If you're quick with calculating numbers on your calculator, that's it. That's your number. And of course, now you have to go backwards, step by step, and calculating everything you can. Because now, for each element, you know at least two different variables. And when you know two variables, you can always calculate the third one, whichever it is. If you know voltage and resistance, you can calculate the current. But the same electric current I, which travels in the last most simplified circuit, will be traveling in the previous circuit. This is the current which travels through the battery. That current splits at the junction point. So we can call it I2 and I3, for example. But again, for each element, when you know two variables, you can calculate the third, and you should be able to see it. For example, here, because electric current has been found before, and because you know the resistance of any resistor, 110 or another one, you can calculate the voltage across each of these resistors. Delta V, let's call it 1. And the same voltage, of course, the same resistor has in the previous circuit. And if you know voltage number 1, you can calculate voltage number 2, which is the same in both circuits. So you should try to practice in seeing connections without using any equations, because that saves time. In this particular situation, I've got all the numbers, so you can practice at home, and then you can check your calculations with these calculations. Question. What do we think? So we've got two circuits, number 1, number 2, or we call them A and B. In one circuit, we have a battery and a bulb, nothing else. You know what? I'm not sure how old is this one. We need a very fresh battery. Oops. Too fresh. Hasn't been used yet. Amazon, the source of the batteries. I wish they would pay me for that. Come on. All right, so let's see. Does it work? Yes. So, and I will have to attach a second bulb. See if it works. Yes. To attach a second bulb to the first one, I need 2 wires. And you have to tell me what do you expect would happen with the brightness. So all I have to just connect it. All I have to do, just connect it. Let's record it for the ages. Bless you. Well, of course, we can reason, not just guess. Or probably just easier to look at. So this bulb experiences voltage of 9 volts. And that's why this bright. And when we connect the second bulb in parallel, which is identical to the first, same resistance, what will be the voltage across that bulb? Well, in parallel, that means it's going to be 9 again. Same resistance, same voltage. What does it mean? What does it mean? Don't move to the right. Same resistance, same voltage. What does it mean? Same brightness. Same. Of course, it does work perfectly when the battery is absolutely fresh, because over time the battery loses its property and the internal resistance might change the effect a little bit. Just give me a second. So first of all, you saw it. Same. And if you thought differently, that means you were wrong. Question is why? You tell me. It's a circuit. See, probably people over there couldn't hear you, so I repeat, the current is cut in half. This statement, I'm sorry, in this particular version of it, doesn't make any sense. Because again, you are too general. Which current? We have a current number 1 here. We have a current number 2 here. We have a current number 3, number 4. These 2 situations, 2 simple circuits, you can talk about 4 different currents. If you just say a current, that doesn't make any difference, doesn't make any sense. You have to be more specific. That's the problem with solving problems. You have to be as specific as possible for every question and for every step. Yes? Again, the biggest mistake you're doing right now is thinking. Don't think. Do. You want to solve it, solve it. Pick a number. Because all bulbs are identical, call them 10 ohms. 10. Good, well, yeah, 10. 10 is a good number. 10, 10, 10. Calculate all 4 electric currents, which possible, I1, I2, I3, I4. Just do it. You can do it, so you do it. If you can't do it, ask what information is missing, what law is missing, or what definition is missing in your reasoning. So, all right. Electric current number 1. 14 over 10, 1.4. Please now calculate and tell me the value for electric current number 3. Anybody, please. It's a general question. You should just calculate electric current number 3 and tell me a number. Electric current number 3. That is electric current which was traveling and is traveling right now when I connect it through another bulb. Okay? So you've got a battery. Well, that battery is 14 volt. This is how this circuit works. Battery, one bulb, second bulb, 9 volt, 10 ohms. So please tell me the electric current number 3 is equal to, how did you find it? So you see, you just said the magic word, equivalent. Equivalent means you have replaced 2 actual bulbs with 1 element. What is the resistance of these single element? What number? Anybody? Yeah. Who are faster? This is connection in parallel. By connecting resistors in parallel, what is happening to the resistance? Decreases. So it will be a half, 10 over 2. Identical bulbs, 5 ohms. So now the electric current, which you're calculating as 14 over 5, which is 2.8, is equal to, which is electric current? I1, I2, I3, or I4? I2. That's the one which travels through the battery in both circuits, in the original and in the equivalent. This is the current number 2, which splits. How does it split? Equal resistances, equal currents. So I3 will be equal to a half of I2, which is 1.4. I4 will be equal to a half of I2, which is 1.4. And of course, we could have used the Ohm's law, right? Because a current is equal to voltage over the resistance. But because they connected in parallel, the voltage is 14 and the resistance is 10. So we have the same number, which makes everything consistent, which is a good thing. So what happened is, when we have added a second bulb in parallel to the first, we decreased the total resistance in half, which means we increased the current drawn from the battery by 2. But that current, which doubled here, again split here in half. So each bulb still has exactly the same current as before, which is equally bright, not just to each other, to the case before. So, what should you take from this? Number 1, don't think. Number 2, be specific. All right. Okay, I just solved it. Next question. It's a very similar situation, but instead of a second bulb, I will be adding just a wire. So I have a battery connected to a bulb. It is on. It is on. So in my previous experiment, I used a second bulb. Yeah. And that's how it worked again. Now I remove the bulb. I'm going to just use the wires directly. So what is your expectation about what's going to happen? All right, if you think the bulb explodes, please raise your hand. Okay, that's a good sign. What do you think?
Wires have no resistance. If you plug them in, it's the same thing as not plugging.
All right, now we can check your prediction. So you were wrong, which is a good thing.
So no resistance on the current goes into them.
So you have two devices connected in parallel. One has resistance, second has zero resistance. So electrons, remember, smart. Why would they go through the resistance if they can go through where there is no resistance at all? So they all go through the wire. No electrons go through the bulb anymore. That's it. And technically, what you have to do is draw a circuit with the bulb and a resistor which has zero resistance and calculate. Okay, that's the answer. And that's not the only possible situation. That's the simplest one. Yeah? We may have more elements together as long as there is a wire presented which has no resistance. This doesn't act like a junction anymore. This element doesn't matter anymore. All electrons, all charges will travel through the wire. So if I close this switch, what happens? Well, actually, I can make it work out. So first, we have two bulbs connected in series, which means they will be equally bright, but dimmer if only one bulb would have been connected. Because when two, see, 1, 2. Total resistance is higher, current is lower. Now what I'm doing is using this wire across one bulb. So what's going to happen? What's going to happen to total resistance? This bulb will not matter anymore. Only one bulb provides the resistance. So the total resistance from this case goes down, current goes up, it's brighter, but now there is no current through this bulb, it goes around it through a wire. This case. In this case, of course, we shortened the whole circuit. So when we shorten the whole circuit, which is not good for the battery, but no current now travels through the bulbs. It goes through the wire. And yeah, if you shorten the battery, eventually it's going to be ruined. It's getting hotter. Well, next situation. So that's not a question. We just had this example actually working, built in. We just need to redraw the circuit. When the switch is open, there is no current through bulb C. So all we have is two bulbs, 1, 2, and that's it. So what's happening to voltage? Well, if we have identical bulbs, identical resistors, the voltage should split evenly. 60 volts, 60 volts. Can we prove it? Well, of course we can. Because the voltage should be equal to a current times the resistance. And if the current is the same because of the type of the wiring, and resistance is the same because we're told so, the product will be the same. So it should be two numbers equal to each other, and if we add them, we should get 120. So, and equally bright. Now, this is a new experiment with 3 bulbs now. What do you think is going to happen to the brightness of this bulb if we close the switch? So I'm going to give you time to think about it. This is a rare situation when you need to think. So, 2 bulbs connecting the battery. I need the third one. And I want it to connect. So this is the bulb A, B and C. C, for now, is disconnected. I need one more wire. As soon as I close the switch or connect this wire, that should or should not, depending on your reasoning, affect the total resistance of the circuit. What should happen to the total resistance? If total resistance doesn't change, current doesn't change, brightness doesn't change. If total resistance increases, current decreases, brightness decreases. If total resistance decreases, current increases, brightness increases. That's the way of reasoning. Or you can just memorize this and don't think anymore. So, by adding an extra element in parallel, how does it affect the resistance of these 2 elements? What do you think? It should change, yes. Goes down because we're given more room for electrons to travel. If the resistance of this part of a circuit decreases, how does it affect the whole resistance? Also decreases. If total resistance decreases, electric current through this bulb increases, it should be brighter. See? Hundreds of years ago, that would have been magic, right? You know, people with batteries and bulbs could have been making lots of money. Now just physics again. See? Now what happened to these bulbs? Well, look at this one. It was bright, now it's dimmer. Why? Well, even the total current increased, but it wasn't doubled. So it splits here, and the current through bulb B, now it's lower than it was before. And of course, we can prove it mathematically. We just have to apply the law, right? Or left. So, well, we made a change. The rule is, if the change has been made, what do? We redraw the circuit. That's it. Now, initially, we had, well, let's call it current number 1, same as 2, current number 1, same current, traveling clockwise. And that current was equal to 120 volts divided by, well, R plus R. When we need to compare something before and after, we actually could pick a convenient number. We believe the actual value doesn't affect the result, so we can pick R equals 10, for example, and work with that. Or just keep R, but in that case, we have to do some algebra. Now, that's a current number 1. Current number 2, which splits here, should be equal to what? Well, it should be equal to 120 divided by the new total resistance, which should be equal to R plus a half of R. Which is what? Which is 240 over 3R. So if you just want to compare, just use a common denominator times 3, 360 over 3R. Clearly, first current is higher. But the current number 3 and the current number 4, I3, I4, they should be equal to 1. What did I do? 360. It should be higher. Why is it lower? It's R plus R, 2R. So times 2, 360 over 6R. Which is, again, going back to 3, 180 over 3R. And that should be equal to 1/2 of I2, which is, wherever it is, 120 over 3R. So, algebra or a specific number. And, well, don't answer this question, we just have it solved, actually. So, scratch it. And electric current in bulb B should be, of course, is the same as in bulb C because they have the same resistance. So IB is equal to IC because in both situations we would have to calculate current as resistance times voltage. But for devices, resistors connected in parallel, the voltage is the same. Same voltage, same resistance, same current, same power, same brightness. Okay, we just did this. So, that's what I didn't do. Let's do it quickly. We've been talking about voltage, 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 voltage. What about electric potential? So, of course, we always set the negative electrode of the battery to zero potential. So this says potential is equal to 0 volts. Same letter V, different meaning. And electric potential along a wire doesn't change. So it's 0 up to this point. Let's call it VB, doesn't matter, still 0 volts. Then it changes. How? The rule is electric potential drops in the direction of electric current or rises opposite to the direction of electric current. So if we have to apply, first we have to say this rule out loud, listen to it, because it involves the word current. It forces us to draw electric current. We need to know a rule for the direction of electric current. Outside of the battery, electric current goes from higher potential to lower potential. So this is the direction of electric current. It splits here, goes back, it splits here, goes back, and electric current returns back to the battery. And inside the battery, electric current travels from a negative terminal to the positive terminal. Well, at least if it's one battery. So now, it means this potential, electric potential, VA, should be higher than VB. Electric current travels from A to B. So VA should be equal to VB plus the voltage, well, B, plus this voltage. Actually, we didn't calculate the new voltage. We only knew the voltage when two bulbs connected. This is a different situation, so we have to calculate the new voltage. And how do we do that? Well, this bulb has resistance of R, 1R. Those two together can be replaced with one resistor with a half of R resistance. That's what we already said, so we know that. How does it affect the voltage? Delta V1, delta V2, which is also delta VB, which is also delta VC. Well, the Ohm's law says voltage equals current times resistance. This is a general law. We can write it twice. For the first bulb, for the second bulb, well, second element. And we can see, because these two elements share electric current. Electric current is the same, only resistance matters. So this voltage should be equal to a half of this voltage. This voltage should be equal a half of that. How do we write it? This voltage, delta V2, also known as delta VB, delta VC, should be equal to 1/2 of delta V1. But together, if we add them up, what number do we get? This voltage and this voltage is equal to what number? 120? 120, yes, that is the number. So, that's the equation number one, and the equation number two is this is not the only possible approach. I just want to show this approach because sometimes it saves time. What two numbers, if you add together, equal to 120, but one should be twice larger than another one? What? Please tell me the answer. 40 and 80. Now, which is which? Is this 40? No, it should be twice of that. So 80, 40. And of course, you can do it algebraically. So that should be 80 volts. This voltage should be 40 volts. Those are voltages. But now we can use this number for calculating electric potential at point A. It should be equal to 0 plus 40 volts. Electric potential VA is equal to 40 volts, which is consistent with the next voltage. What is voltage? It's a magnitude of potential difference. So potential here is 120, and the voltage should be 80, which is equal to 120 minus 40. Again, everything is consistent. All right, and I have a slide with all these numbers for both cases. Moving on. Okay. I want to use this opportunity to talk about an important fact. So this is what I want to do. I want to connect this bulb to the battery. Now I want to use longer wires. Why? You'll see. To connect the second bulb to the first one. What's going to happen? Nothing. We saw it already. So this is not circuit like that. In this picture, the bulb is in the middle, and the battery is in the middle between the bulbs. So, is this circuit different from that circuit? What about now? What about now? Oops, that makes difference. You have to keep everything connected. All right. It's still the same circuit. This is just a picture. The actual physical realization of a circuit could be many, many different ways to actually build this circuit equivalent to this picture. Which means actually we can redraw the picture in any way we like. We just have to keep all the connections the same. For example, I can redraw this circuit, bringing all resistors on the same side like this. Let's call it A. And I'm moving two other resistors on another side. It's exactly the same circuit if I keep the same values. 40 volts, 40 ohms, 120 ohms, 50 ohms, 50 ohms. We don't have to do that, but sometimes it helps. Well, calculate everything. What can we calculate? Equivalent resistance, every single current, every single potential difference. But we also can calculate potential. That's what I want to do. I want to know potential VA, and I want to know potential VB. And if I know those potentials, if I need, I can calculate potential difference between A and B. Why would I need it? I don't know. Just as an example that we could do that too. Well, how do we calculate electric potential? Since we talk about electric potential, we always start from assigning 0 to a certain point in a circuit. And normally, that's a negative terminal negative electrode of the battery, which makes electric potential here, 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 all up to here, all up to here, all up to here, 0. Now, there is certain voltage. Let's call them 1, 2, 3, 4. So it's going to be 1, 2, 3, 4. There is certain voltage, number 1, across the first resistor, and the electric potential at point A should be equal to 0 plus this voltage. Okay, now we know what we need to find out, this voltage. There is a certain voltage, delta V3, across the third resistor, and the electric potential at point B should be equal to 0 plus delta V3. Technically, I should have drawn a current. Or in this situation, there's electric current goes through the battery, splits. And well, now we got to start calculating voltages. The good thing about elements connected in parallel, as we saw in the experiment, they do not affect each other. So here, I have two identical resistors connected to the battery. What does it do to the total voltage of the battery? How does it split? Evenly. So that should be 20 volts, that should be 20 volts. Oops. That's not the right branch. It's 40. I'm going to do 50 and 50 first. Yeah, splits evenly, 50 and 50. So that should be 20 volts, and 50 and 50. That gives me VB. VB. 20 volts. And now, actually, I don't want to fit it inside. I want to keep it outside because I can. It doesn't change the circuit. 40 ohms and 120 ohms. Now the voltage number 1 is not equal to the voltage number 2. However, I can tell you, and you can tell me, the relationship. First of all, if we add them up together, we should get 40. That's a total one. However, delta V2 is across a resistor with a higher resistance, so it should be also higher than delta V1. But that's not only one thing we can say. We can actually say the exact coefficient between these two voltages. There is a number which relates these two voltages. Please tell me that number. Yes? You asking or you're saying? You're saying. All right. And of course, we should be able to prove it quickly. And how do we prove it? Well, electric current here, let's call it I1, is the same for both, right? So delta V1 should be equal to electric current number 1 times 40. but delta V2 should be equal to the same electric current times 120 same electric current. So for example, if you have these equations, you can divide them. Electric current is the same, it's getting cancelled, and we get this coefficient 3. So now we can ask, what two numbers, if we add them together, will give 40, but one is 3 times greater than another one? What are those two numbers? Anyone? And 10 and 30. If you're not sure, of course, you can solve it algebraically because it's a system. The equation number 1, the equation number 2. Which is 10, which is 30? This is supposed to be 10 because it's lower. This is supposed to be 30 because it's higher. And that gives us electric potential A, 10. So now that's a VA. Now we can calculate potential difference, delta VAB. We can't do more because if we have a circuit like that and we have a multimeter, we can actually measure that potential difference. All we have to do is connect one electrode to point A and the second electrode to point B and read the number. And what should we read? 40 minus 20 minus 10, 10. But of course, we can calculate every other thing. We just have to use new numbers. If we know the resistance, if we know the voltage for every single resistor, we can calculate the power if you want to. We already have, we can calculate electric current, right? So. All right, I did this. Okay. Since we skipped the question number 7, that should be the question number 7 right now, I suppose. I want to ask it. So we have a more and more complicated circuits. Now this circuit has 1, 2, 3, 4, 5 passive elements, 5 resistors, and 1 active element plus a switch. Initially, the switch is opened, and the question is, what will happen to the brightness of the bulb A when we close the switch? That's it. I'm going to give you time to reason it through, to choose your answer. What do we have? On one side, we just have 2 bulbs connected in series, and wherever it is. And on another side, we have I can just check. Good. 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 So now what do? I have to connect this one, the second one, and then I have to connect this one in parallel to this one. We had this experiment done before. We had two bulbs and we connected the third one and we saw what was happening. The brightness was changing. But now we talk about another situation. So, let's do the magic. So I'm going to connect and disconnect this bulb again. You should be looking at this bulb. Disconnecting, connecting, disconnecting, connecting, disconnecting, connecting. Do you see any change? No. What change is, where change is happening is here in this circuit. Like it was before. Two bulbs equally bright, and then one becomes brighter, second becomes dimmer. But it doesn't affect anything on another side. Why? Same reason. The voltage of the battery is a fixed number, and no matter what I'm doing with this side of a circuit, it doesn't affect the voltage across the second side of the circuit. Bless you. So what does it affect? Well, it affects the total resistance. It affects the total current. So the total current will be different, and the current in this part will be different. But the current in this part is fixed by the value of this battery and the resistances of these resistors. So no effect. And by the way, I've got also another version which I want to do right now. It's not just toys. We can use actual devices. These are bulbs, identical, all 100 watts. And I want to connect first these two in series. So the electric current should travel like this, like this, like this, like this. Yep. Now I will add a third bulb in parallel to the second. The behavior is exactly the same as we saw before. Total resistance drops, so the brightness of this bulb goes up. But here, equally dim. But if I have another bulb connected to a power outlet, no matter what I'm doing here, will not affect the brightness of that bulb. So exactly like in this situation, exactly like in this question. Every time we should look at the specific connection and this specific connection tells us. Well, first of all, we have to redraw the circuit. And we do have time for that. Here we only have two bulbs also. The third is not a part of a circuit. That's the first situation, situation number one. And the electric current we want to compare is this one, IA. Situation number 2 is different. Same battery, 2 bulbs. Now we have 1 bulb like this, and now we have 2 bulbs connected in parallel. But now we have to look at electric current IA. What's happening with other bulbs doesn't matter. And the electric current through bulb A in both situations is equal to 120 over 2R. 120 over 2R. Electric current through the battery, of course, will be different. Yes?
Okay, yeah, maybe you're about to answer it, but my question is, in the second situation, the side on the right now pulling more current?
Yeah, and that affects the total current. The current through the battery will be different. This is only the current through the bulb A or another one. But the current through the battery, let's call it A1 and A2, will be different. Let's call it, what did I say, I1, I2, IB star. Current number 1 through the battery equals current through A plus current through B. Current number 2 in a second circuit through the battery will be equal to current A star plus current B star. Well, these two are the same, but these two are not. They are different, which affects the current through the battery, drawn from the battery by the whole system. And we know that the current in a second situation through bulb B will be higher than the current in the first situation through bulb B. But we can analyze those two parts of the circuit independently because they do not affect each other. And that completes our class today. Thank you. So again, tomorrow I'm going to finish some examples and then questions and answers, and then hopefully the new topic.